We've got all these circuits in place, like for example what we did in our mid-semester exam with regard to systems which can handle data from sensors. But more so, when you look at the computational side of things, we want to talk about circuits which can do arithmetic, which can crunch numbers, as I said yesterday, right? Remember, when you have a computer, the processor, the computer processor, in every processor you have got a little corner of that processor which is known as the arithmetic logic unit. Now, that arithmetic logic unit is used for processing or crunching numbers. So there's adders and there's subtractors, right? Now, with adders and subtractors, you have circuits or digital circuits which can add binary and subtract binary. So the objectives of this lecture is to, we want to discuss the fundamentals of arithmetic logic circuits. We want to design half and full subtractor logic circuits, and we want to differentiate between half and full subtractors. So basically, we're doing the same thing as what we did yesterday. We're doing the same thing as what we did yesterday, right? And except for the difference is that we are looking at subtractor circuits rather than adder circuits, right? And you'll see a lot of similarity between what we have here and what we have in the adder circuits. Now, a recap. As part of this lecture, you should be familiar, as part of this lecture, you should be familiar with the design of half adder and full adder logic circuits. You should be familiar with truth tables, Boolean algebra, K-maps. You should be familiar with sum of products and sum of min terms, product of sums and product of max terms, and minimize form of a function. Now, all these tools, it's like a toolbox, as I mentioned yesterday. We've learned all these tools, how to use K-maps, the Boolean algebra theorems. We've learned about truth tables. We've learned about, the minimized forms of the function and so forth, right? But all those tools, we've got to apply it somewhere so that we have something useful which comes out of it. And one of the applications is to build arithmetic circuits, circuits which can do mathematical processing like addition, subtraction, multiplication. So we did the major part which you need to be familiar with is the design of half and full adder logic, like what we did yesterday. All right, let's start off with subtraction. We did addition yesterday. We want to start off with subtraction. Now, with subtraction, we consider let's consider the following simple decimal problem. We want to do 25 minus 18, right? Now, once you become familiar with what's happening here, we will be able to follow through with what is happening in terms of our binary subtraction. So 25 minus 18. So firstly, when you do a 5 minus 8, right, you can't do that. So what are you going to do? You've got to borrow. So the right hand side has got to borrow from the left hand side. Okay? The right hand side has got to borrow, the right hand column has got to borrow from the immediate left, its left. You can't go and borrow all the way left, you've got to borrow from the immediate left, right? So for the right hand column, from the left hand column, the 25, you cut the 2, you've got a 1 left, right? That's a leftover. And the 1 is borrowed, so that's a borrow in. You're borrowing in, right? You're borrowing in. And for the 2, that 1 was a borrow out. So there's two things happening. There's a borrow out and there's a borrow in. Just like yesterday, there's a carry out and a carry in. In this case, there's a borrow out and a borrow in. Okay? Now the borrow out of the left column is the borrow in of the right column. Right? Okay, please make sure you get familiar with that particular terminology. Now let's have a look at some subtraction rules. Now you have 0 minus 0 is equal to 0, so you borrow a 0. 1 minus 0 is equal to 1, there's no borrow involved. We've done all these rules before, by the way, but this time we are trying to keep in track the borrow. What is the borrow happening? Okay, all right. 1 minus 1 is a 0, that's a borrow of 0, and 0 minus 1 is a 1, where you've got to borrow a 1. Now, just like yesterday. So I think if you look at yesterday's lecture and you look at this lecture here, you start to become familiar with what is happening. All right. Now, let's now convert our information, what we've just processed, into, let's now look at the information which we have just spoken about and process that in terms of a truth table. All right. So let's now draw the truth table in your exercise book. And what we will do is, based on those rules, we will develop a half subtractor circuit. So based on the subtraction rules which we have just done there, we will develop a half subtractor circuit. You'll see that a lot of things start to become like very, very similar to yesterday's notes, if you attended yesterday. All right. So let's draw the truth table in our exercise book. We've got A, you've got B, you've got difference, and you've got borrow. All right. And because there's only two inputs, you have 0, 0, 0, 1, 1, 0, 1, 1. Right. Now, let's now look at this here. You remember this? And I'm going to flip over to the document camera now. Okay. 0 minus 0 is a 0, borrow is 0. Let's do these two lines at the bottom first, so that 1 minus 1 is 0, borrow is 0. 1 minus 0 is a 1, borrow is 0. 0 minus 1, that's the tricky one. 0 minus 1, according to our rules, is what? It gives us a 1, and the borrow is a 1. Okay? All right. Okay. Now based on those rules, let's now devise a formula for D. We can, of course, one of the methods would be to do a 2 by 2 Kano map, right, for difference, right? But you can just look at it, and by now you're familiar. What truth table does D represent? What is that the truth table for? That's XO, right? That's XO again. Just as we had XO yesterday, we have XO again today. So we have A XO B. That's the difference. Now borrow. Borrow out. How would we represent borrow? Let's use our sum of products method. If we want to use sum of products method, borrow would equal to what? It'll be A bar and B. Yeah? And in the end, our particular circuit, there is A, there is B, okay, and that's again A. Got to put a NOT gate there. That's B. Okay, so that's the difference. That's the borrow out. There you go. That's your circuit. And that is your circuit of a half subtractor. Now, just like yesterday, most of the definitions remain the same. Most of the definitions remain the same. So, you have the word half subtractor, and you have the word full subtractor. And what do those mean? Well, basically half can only process one bit at a time, and it doesn't allow for borrow in. Okay? Alright, only looks at the borrow out. Now let's flip back to our PowerPoint slide. There we go. Our circuit, logic diagram. And because we use it so much, right? Now, as I said, this particular circuit is a half subtractor circuit. It is not able to utilize the borrow in our inputs. In reality, if you look at a real real subtraction problem in binary, you will need to utilize that borrow. But in this case, it is not able to. So this is known as a half subtractor. It's like a half cooked thing. That's the block diagram. Very simple. A block diagram for a half subtractor. And we'll be using that. And what it does is, all it does is A minus B, where A is 1 bit and B is 1 bit. Alright? Okay. Now let's talk about a full subtractor. Half subtractor can only handle 1 bit subtraction. Consider the binary sum 1 0 minus 1, right? Or binary subtraction problem 1 0 minus 1. Now, how do we do this? We've got to cut, borrow from the left hand column, right? Bring it into the right. 1 0 minus 1 is 1 0 minus 1 is what? 1 0 is a 2. 2 minus 1 is 1. Right, and 0 minus 0 is 0. So that's the difference over there. So in the end, what we see is that it's A minus B minus borrow in is equals to difference and borrow out. That is the formula as shown in red. Okay, borrow out of the left column is the borrow in of the right column. Okay, so let's now do the truth table for. Let's now do the truth table for the sum, for the full subtractor. Okay, remember that formula. A minus B minus borrow in is equals to difference and borrow out. Right, difference and borrow out are two different columns. So you've got A, so put that in your exercise book. That truth table is empty, we're going to fill that up. B, borrow in, difference, borrow out. Zero 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 one 010 011 100 101 110 111. Okay. All right. Let's turn over to the document camera. Okay. All right. So that's our truth table. We're always able to easily populate our input side simply by means of, if there's 3 inputs, you just put all the possible combinations there. Okay. What do we get on the output side? How do we know the difference? Well, there's 2 things which are being done in parallel. 0 minus 0 is 0. We've got to do 2 things. Remember it was, I'll show you the formula. One slide back. Can you see the one in red? It's a second last line. It says A minus B minus borrow in. Can you see there's 3? A minus B minus borrow in is equal to the difference and the borrow out. A minus B minus borrow in. 0 minus 0 is 0. 0 minus 0 is 0. Borrow is 0. Right. 0 minus 0 is 0. Right. Now, 0 minus 1 is So basically there's an interim answer. It's like saying 5 minus 3 minus 2. Right? Okay? So how are you going to, if somebody, let's say 5 minus 1 minus 2. How are you going to do that? Firstly you'll do a 5 minus 1 equals 4, and then that middle interim answer. 4 minus 2 gives you 2. Yeah? Alright, so there's an interim answer in the middle, and then you've got your final answer. Alright? Okay, so same thing goes over here. 0 minus 0, A minus B is 0 minus 0 is equal to 0. 0 minus 1, interim answer minus 1 is give you, let's remember our rules. What are our rules? 0 minus 1 gives you a 1, right, with a borrow of 1. That's how you do this. Okay? Now, 0 minus 1, right, what is our interim answer? 0 minus 1 will be difference of 1 and borrow of 1. Now, we're going to minus a further 1 from that. Right? Okay? Oh, we're going to minus a 0 from that, not a 1. A 0 from that. 0 minus 1 is 1, 1, right? Difference of 1 and borrow out of 1. Minus 0, no changes, so you'll still stay at 1, 1. Yeah? Okay, so remember there's an interim answer in the middle. It's A minus B, just like how I said 5 minus 2 minus 1. So 5 minus 2 is 3, 3 is the interim answer. Then minus 1 gives you, gives you the final answer, which is 2. Alright? So let's do the next line. 0 minus 1, this one gets interesting. 0 minus 1 is a difference of 1 and a borrow of 1. Right? Now, 1 minus another 1 now, right, gives you what? Gives you a difference of 0 and a borrow of 1. Okay? Alright? So remember, interim answer was 1. Difference was 1. Remember, you've got to think of it like a vertical problem. Like a vertical problem. You know this, we always write, you can write 23, look at my hand, you can write 23 plus 45 in a straight line, 23 plus 45, or you can write down 23 plus 45. So when you think of that fourth line, or all the lines over there, you think of it as vertically. So, but you have to do it in 2 stages. 0 minus 1 gives you 1 borrow of 1, then okay, over here your difference is 1. 1 minus 1 gives you a 0, but the borrow carries on from the last interim result. Okay, alright, let's now do the next one. 1 minus 0 is a 1, and then 1 minus 0 is a 1. Remember, the borrow is 0. 1 minus 0 is a 1, right? Interim result 1 with a borrow of 0. And 1 minus 1 is 0 with a borrow of 0. 1 minus 1 is 0 with a borrow of 0. 0 minus 0 is 0 and the borrow from last time continues. Now this one, let's do this one. 1 minus 1. 1 minus 1 is a 0. Borrow of 0. And 0 minus 1 is a 1 with a borrow of 1. There you go. We've just done that. Okay? Alright. Okay. Now, that's not good enough. I mean, just doing the truth table does not give you the circuit. You've got to do Kano maps, you've got to do, like in our 2x2 case, in our half subtractor case, hey, that was quite simple because we didn't need to do a Kano map. It's so simple, you can just look at it and say, oh yeah, that's an XOR gate over there. Alright? Okay? Alright. Now, what do we do from here? Let's now find out what our difference is. Okay. There we go. Set. So we're doing a Kano map for column D, yeah? For output D. There's 2 outputs. 2 outputs, that means there'll be 2 Kano maps. Number of outputs is equal to number of Kano maps. Okay. For those of you who want to do this, yes, you can always number your cells 0, 1, 2, 3, 4, 5, 6, 7, and let's go. That's 0, 1, 2, 3, 4, 5, 6, 7. All right. So what do we end up with over here? We end up with this situation. Now, as I mentioned yesterday, and I gave you a piece of homework yesterday, right? Can you see the ones are arranged in such a manner that it's like a squitch situation. Nobody wins. The whole idea of doing the Kano map was to reduce or minimize. But in this case here, that Kano map, the ones are configured in such a manner that there is no minimization. We call this a checkerboard situation. This Kano map, when it's arranged like that, right, and all the ones are just a single groups of one, there's no minimization possible, right? This particular situation is known as the checkerboard situation, and this is the equation, and I'm deliberately not giving you the proof from there to there. That's part of your homework, and that might come in your test number 2, or it might come in your final exam. So just note that down somewhere in your exercise book. You guys are here, so I'll let you know. All right, that will come. Prove that that Kano map is equal to A XOR B XOR C. Oh, sorry, it shouldn't be C. That should say B in, right? Yeah, that should say B in. Okay. Right. Now, let's now look at the borrow out. Another Kano map. Okay, so let's say A over here. Hey, I'm just going to, just to show you guys that we don't have to follow the same pattern, eh? I just want to show you guys we don't have to follow the same pattern all the time. I'm going to put A this side here now, and I'm going to put B, use a different color, B in on that side. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. I just want to show you, hey, the Kano map does not have to be A, B all the time sticking together. Right? B can hook up with B in as well. All right? Okay? So you don't have, and A doesn't have to be on the long side. You can even draw the Kano map. Remember, I've probably drawn you this. The Kano map which goes like this way, long, vertical. Yeah? All right? 2 on the horizontal and 4 on the vertical. So just to show you that we can change things. All right? There we go. Okay, so I think in this particular situation you'd say, I'm not going to label the cells. If you want to, you can label the cells. Labeling the cells is not the answer. It just, what it does, it helps you go faster, right? But if you already know the cell numbers, you don't need to label it. It's only that I'm teaching you, because I'm teaching you, that I've got to show you each and every little step so that you don't get confused how I got the answer. Anyway, okay, so that's, hey guys, if you look at this particular grouping, that looks very familiar. That looks just like what we did yesterday. Can you see the similarities between half subtractor and half adder, and then the full adder and the full subtractor? Yeah? All right. So there we go. Okay. And what is B out equal to? B out is equal to B out is equal to, let's think about this. There will be B in, or A bar B in, or A bar B. Now, this is where it comes in, guys. You can see that clearly? Is that all right? Okay. Now, for those of you And because you guys attended yesterday's lecture as well as today's lecture, I'll let you know I'm going to heavily test you guys on, during test 2 and during the final exam, we're going to heavily test you guys on adders and subtractors, half adders, half subtractors and so forth. Now, I want you to for a second, just flip over your pages of your book, look at yesterday's proof. Firstly, just have a look at the derivation for half subtractor and half adder. So, in your notes somewhere, what is the sum for half adder and what is the difference for half subtractor? It's both A XOR B, yeah? Right? In both cases. So you flip over the book if you were yesterday, right? The other thing I want you to look at. Have a look at this thing here. Okay, there was sum, and in half adder, what's the other thing? The half. I'm talking about the halves now, right? There's sum and there's what? There's carry out. Yeah? What is carry out in half adder? It's A and B, right? Yeah, it's just A and B, or is it A or B? Straight up A and B. Yeah, the carry out. What about the borrow in the half subtractor? It's A and B bar. Subtle change, just one little change and it became, the half adder became a half subtractor. Right? I want you to look at the circuit now. The circuit between half adder and half subtractor. How many of you guys were there yesterday, in yesterday's lecture? Right, pretty much everyone, okay, alright. Now, subtle change. Now let's move to the full guys now. Let's move to the full adder and full subtractor. What is the sum function in the full adder? What is the sum function in the full adder? Sum is equals to A XOR B XOR carry in, yeah? And what about over here? What is the difference function in our full subtractor? It's A XOR B XOR borrowing. Can you see it's almost the same, it's a replica, just a subtle change and bang, the whole circuit changes. Right, so, right, okay, now, what is for carry out? What is the equation which we found for carry? Remember there was an error and then I corrected the error and then I said, hey, let's have a look at this. And then I wrote it in black yesterday, right? It's still fresh in my mind from yesterday's lecture. All right, what is the carry out? Yeah, what is the carry out function for the full adder? It's A, okay, no, the function without the XOR. Remember I gave two functions. Let me just pull this out from yesterday. There we go guys, this is yesterday's note. And I said, hey, you've got AB, carry out is equals to AB or BC in, right, or AC in, yeah? Okay, and I said, hey, you can rewrite that as such, AB or C in and AX or B, yeah? AX or B, and why I said we got to do that? Because we want to bring it into a form deliberately from a design point of view. We want to utilize the XOR gate because our half subtractor and half adder uses the XOR gate. Yeah, so we want to utilize the same gate. So, and then a lot of you guys were confused. How can we get from here? How can we get from here? This is yesterday's notes, guys. How can we get from here to here? How can we bring the XOR in? And then we went and did this long proof, right? And I said, hey, so I hope you cut that wrong answer out and the wrong groups out. That's the correct groups. I said, hey, if you group it like this, you'll get that. And that can be brought here. And then that is equal to that by means of all this derivation. Now, the exercise for you, for your final exam purposes, the exercise for you is, if you look at this Kano map, look at how we got that. Right, look at this Kano map. This for the full adder, how we got from here, right, and how we ended up with the XOR, right, and the proof. Now I want you to now just put a note down. That's your home exercise, right? By the way, this, I think I'm pretty sure this, all these lectures, do the lectures get recorded properly or is there a problem? I just want some feedback. When you guys go and do the video lectures, are the lectures alright or are parts of it missing and is it haywire? Have you guys been watching? Anybody watches the video recordings and all these things? Not yet? Alright, so because you guys, I presume you already attend the lecture, so no need to watch the videos. Alright, so I want you to look at that bottom part, compare the borrow out with our carry out from yesterday. Remember, in subtraction, it's always the borrow. In addition, it's always the carry. And then how can we get that equation? B out is equals to borrow B times B and borrow in, or A bar and borrow in, and or A bar and B. How can we get that into a form which utilizes XOR? Right, so that's the question. I'm not going to give you the answer, because that answer you'll have to do in your final exam. Alright, okay? Alright, so, and the working is already in yesterday's note. Of course, you've got to play around and, you know, change it some here and there. It's already in yesterday's note. So if you missed out yesterday's lecture, I would say, hey, quickly go and have a look at the video recording and you'll be able to pick it up there. Alright? Now, let's come back to our screen and I'm going to finish off the lecture very shortly. That's the block diagram. Right? For full subtractor, there's 3 inputs. Just like full adder. 3 inputs, 2 outputs. Half adder and half subtractor, 2 inputs, 2 outputs. Full adder and full subtractor, 3 inputs, 2 outputs. Right? Now, the bottom part is using 2 half subtractors to make a full subtractor. Right? Using 2 halves to make a full subtractor. Right? Okay? And of course, we've got to use an OR gate there as well. Right? That's the key part. And then the final circuit. That's your final circuit. But can you see, this is the confusing part and that's the part which I've given for your homework and further study. And I won't give you the answer when we come in week 8. That's, as I said, you've got to do that. So please make a note of this, alright? Okay? As I've mentioned, when you look at this, there is no XOR here for your borrow out. But when you look at this, XOR has been utilized for your borrow out. Okay? Alright, so the proof, alright, and how you get from that point to that point. Okay guys, that's it for this half of the semester. That's your final slide for today. I just want to have a quick chat with you guys with regard to how the course is going. You see, the first half of the course we were doing combinational. We're going to have 1 or 2 more PowerPoint slides when we come back in week 8, right? Fair enough. We'll have 1 or 2 more slides. We'll learn about multiplexers and demultiplexers, right? In fact, for these 2 topics, the adders and subtractors, they were not covered well inside the lecture notes which were already there. By the way, these slides are already sitting on the system. It's already sitting on the Moodle shelf. So if you want to have a look, you can have a look. But I've made the slides as usual in such a way that the answer and the proof is not there. You've got to come to lecture to get the working. You got the final answer, you got the final circuit, but the working and the proof is missing. So only the students who attended today have got the working and the proof. Alright, so we'll do a few more. So this was not covered inside the, the PDF files. So I had to create new PowerPoint files for this. Okay, we're going to look at 1 or 2 more combinational circuits. This part of the first 7.5 weeks or 8 weeks is known as combinational logic. Right, we sort of fell 2 lectures behind because 1 lecture was cancelled due to the tsunami drill, and 1 lecture was cancelled because we had our midterm exam. So we sort of missed out 2 hours of lectures. And 2 hours is like 1 week. In 1 week we only have 3 hours. Yeah. Okay. And the other thing is, after that we will move into something known as sequential logic. Sequential, slightly different. Sequential logic deals with memory, how to store data, right? Still using NAND gates, still using AND gates, OR gates, but the circuits become more and more complex. They become more and more complex. Like if you look at this circuit, that's slightly complex now. Compared to what you guys were doing in the midterm exam, suddenly after the midterm exam, can you see now it's starting to become more complicated. Because you can't build a calculator. Remember, one of the objectives was, hey, at the end of the semester, you'll be able to build a calculator which can do at least addition and subtraction. You can't build a calculator if it doesn't have memory. You've got to store the answer somewhere. Yeah? So we're going to move into sequential logic. And what I would encourage you guys is, you guys are already here, don't skip lectures. Don't skip lectures. The moment you skip lectures, you start to fall behind. And when you say that, hey, I'm just going to watch the video recording, fair enough, that's okay. That's only in an emergency situation you need to watch it. But if you say you're going to watch the video recording, you'll get behind very quickly, because one recording is 1 hour. And in order to absorb that 1 hour of recording, it actually will take you 3 hours. Alright? It'll take you 3 hours. It's better to come to the lecture. So that's it.